Take a look at Venn diagrams, which can be tricky at times, but we're going to break them down into a little bit easier of a system. Venn diagrams are going to be those circle images that I've been showing you. If it's inside the circle A, then it belongs in set A. If it's inside the circle B, it belongs in set B. And if it's in that overlap, it's in both. And then anything in the rectangle that's not inside the squares would be pieces of the universal set that are not found there. So if I want to illustrate a set for a Venn diagram, I want to draw a diagram for the sets with the Roman numerals in each region. Then I'm going to use those Roman numerals to list the regions described by the set. Then I'm going to find the set of numbers that correspond to it and shade the area. And so if I look at example 1, I have a Venn diagram to illustrate the set of A union B complement. So to do that, I'm going to have to draw the diagram and label each area with a Roman numeral. So this is area 1, area 2, area 3, area 4. From that diagram, I want to list the regions that make up each set. So the universal set has everybody in it. If I look at the red circle, I have 1 and 2 in the red circle, and then in B, in the blue circle, I have 2 and 3. So you'll notice that's how I defined A and B. So I'm going to use those steps, and I'm going to say, okay, well, if they're in either A or B, that would be 1, 2, and 2, and 3. That's missing an I there. And then the only region that's left out, because to find the complement, I need to say, okay, what is in this diagram that's not in the list of 1, 2, 3? And that would just be 4. And so then I want to shade the region. So 4 is found outside of the circles, so I shade outside of the circles. So if I wanted to draw the diagram to illustrate the set of A and B complement, then I'm going to need to redraw that Venn diagram. So this isn't like a list I'm giving you, I'm just naming the regions in the diagram. From that diagram, I've got my universal set, my A and my B from earlier. If I want to find the set in A and B complement, I have to first find B complement. So what are the things that are in the universal set that are not found in set B? Well, that's 1 and 4. Of those regions, what is also in set A? So I need to know what is in both sets, which is just the number 1. And then I would shade that region. If I have 3 sets, the number of regions that I have increases. So what does that actually look like? Well, that means I have 3 sets in play. I have set A, set B, set C. So I'm going to draw a picture that represents having 3 sets, and I'm going to use Roman numerals to describe the areas around them all. So for part B, I want to simply list the regions that make up each set. So U, A, B, and C. So all the things in A are 1, 2, 5, and 4. And then B, 2, 3, 5, and 6. And then C is going to be the values in C. So I'm just listing that out. Then to find B and C, what are the things that B and C have in common? That's going to be 5 and 6. So if I wanted to find the complement of that, I would take 5 and 6 and remove it, and I would list all the other items in the universal set. Then if I wanted to find A and say, what does A have in common with that set? I'm going to go back up to A and say, okay, what does A have in common with this list that I just made right here? Well, the only thing A has in common is going to be 1, 2, and 4. Then I'm going to shade the regions. Now, what if I want to do this? This time I want to say, here's the shading. How do I describe that shading? So I'm looking for items that are found in B that are not found in A or C. So I would write that as either B, take away the items that are in both A and C, or take everything that's not in A or C and then make that up with B. So if it's not in A or C, it's in B. And so then the list of items is basically going to wind up being B. So De Morgan has a couple of laws that he has made. And the first one says that the complement of the union of two sets is equal to the complements themselves, and finding their intersection. The second law says if I'm taking the complement of the intersection, that's going to equal the union of the complements of the sets. That may seem weird, but let's see it in action. So if I have my universal set, this is the list that I have, then I have items in A and B. If I wanted to find the things in A and B and then take the complement of that, that's going to be the same as the complement of A or the complement of B. Let's see how it works. So A and B together are going to give me that list. And then the complement of that means what is in the universal set that is not in A and B. So that's going to be Chancellorsville. So that's what I find using the first way. Now if I find the complement of A, so meaning what is in the universal set that's not in A, same thing with B, I wind up with the same answer. So I've basically proven that theorem. And so similarly, if I want to approach it from the other symbol, then I would take and say, okay, I need to find the A and B complement, so what is not found in that group, and then compare that to not A and not B. So when I do that, I get A and B as Gettysburg and Shiloh. The complement of that means to go back to that U set and cross out Gettysburg and Shiloh, which leaves you with this. Then if I say the complement of A, so what values in the universal set are not found in A, what values in the universal set are not found in B, and then find the list of both of those combined. And so I see I wind up in the same place. So let's look at how to use Venn diagrams to show this. So same thing, but proving it with the Venn diagram instead. So this time, I'm going to shade the complement of A and B, which is the universal set. Then I'm going to look at, okay, that's what I have. And I want to shade region 4, which is outside of it, to give me the complement of A and the complement of B. Notice these images look the same, but following different lines of theory. So I can then say that the sets are equal. If I want to use Venn diagrams to show the equality of these sets, whew, that's a lot of sets, then I'm going to have to break it down and say, okay, if it's in A overlapping with B, that would be found in those areas. 1, 2, 3, 4, 5, 6. Of those, 4, 5, and 6 are also found in set C, which means my answer is 4, 5, and 6. And so that is what I shade. Now I use the same reasoning, applying the law, and I wind up at the same answer. So this really isn't something you're going to see in ALEKS per se, but this is something more along the lines of proving it visually as opposed to proving it analytically. So let's find the cardinality of the union set, which is really nice. So if I look at the cardinality, that's just the number of items in the list. So if I look at it and I start working on cardinality, then I notice that 6, 7, 8, and 9 are in both of sets A and B. So I'm going to basically put these into their Venn diagram. I'm going to put all the items in A that are not in B in the red circle outside of the overlap. And I'm going to put all the numbers that are outside of the overlap of A and B inside the blue circle, but not in the overlap. And I notice there's a pattern here. So from the diagram, if I'm purely looking at the number of items in the set, I have 9 in A, 7 in B, 4 in the intersection, and 12 between both sets. So if I look at that reasoning, then the number of sets would be the number in A plus the number in B minus any overlapping items. What does that actually look like in practice? Well, I have 100 randomly selected freshmen, and 42 are taking a math, and 51 are in English class, and 12 are taking both. Well, if I wanted to find the cardinality of that, I'm going to take my 42, take away 51, and then, 42 and add 51, and then take away the overlapping pieces there for A and B, and that's 12, so I get 81. And that is the end of the lesson.